Welcome to Modern Physics Lab number 5, where you could make your own physics lab. Here we're going to deal with free fall and kinetic energy. So our problem was that we're going to model a frisbee falling from rest, we're going to predict its motion, and then we're going to describe some things about its kinetic energy. We're going to be mainly using the Newton's second law and our kinetic energy formula. The major assumptions that we make is that our system would just be the frisbee and our surroundings will be everything else. Our net force will be equal to the weight force from gravity plus the drag force. And also we assume that there is no heat transfer and no potential energy in our system. So our results were that our model with and without drag actually over predicted our motion. But when we added in a non-zero initial velocity, our model improved. It actually reached terminal velocity faster when we added a non-zero initial velocity. Also, our kinetic energy was always greater than zero. And then another thing to note, our drag force started at zero, but then increased while our weight force stayed constant, which is exactly what we should happen by our fundamental physics principles. So just quickly, our axis and origin. Here's our origin point. This is our frisbee that we're dropping and using our capturing the motion with tracker. Our positive y direction is this way. Our negative y direction is this way. So we dropped it from rest and dropped it down. Just when you're building your computational model, again, this is just Newton's second law in Python code. We've seen this many times before. This is our position formula. Again, something we've seen a lot before. Here, two things to notice is that the weight force, again, this is just the force of gravity in Python code, and our drag force right here, we're using the b times the square of velocity. B times the square of velocity. So that's very important because this is how we get our drag force. We're going to talk about this B constant in a little bit. So again, some of our initial conditions were that our ball's mass was 1.125 kilograms. Our ball's position, or its initial position, is right here. Two things to really point out though: the initial velocity. The first way we modeled it was with our initial velocity at 0, 0, 0. But in actuality, after going back through tracker, we realized that our initial velocity is probably a little closer to this. In the next slide, we're going to show you how we actually calculate this, this true initial velocity. Also, getting back to our B constant, our B constant was 0.4114, and this is found by fixing the final position of the model data to align with the observed data. So in reality, our model isn't really a model because we use a lot of data from our observed data. And again, the last thing to emphasize right here is with the kinetic energy formula. K equals 1/2 times the ball's mass times the magnitude of the ball's velocity squared. That's just our kinetic energy formula. So to actually get our actual initial velocity, we actually went to our tracker data and subtracted our first two position points and divided by the difference between our first two time points to get our actual initial velocity. So some things we see with our predicted motion versus our observed motion. So obviously our model with no drag is very, very far from where our observed position data was. So what we did there was we added in a drag force using that equation of B constant times the magnitude of velocity squared. We added that in, as well as we added in a non-zero initial velocity. These are just some tricks that we picked up when we did this lab a couple weeks ago. And what we find is by adding in those two things, this green line, our model that has drag and non-zero initial velocity, is much, much closer than our model that has no drag and has an initial velocity of 0. But even still with that, we still noticed a large amount of error. So some reasons for this is, first, it was very difficult to ascertain the center of mass from the video. When the frisbee was falling, it was very blurry. Also, we notice that we have a very, very large B constant, much larger than our second lab, and that might detail some potential errors in the code. Also, it's very hard to see the video at the very beginning because of the way it was shot. Last thing to talk about is that our kinetic energy. Um, so you notice here that this is a graph of our kinetic energy versus time. Our kinetic energy is always greater than zero, and which makes sense. Also, the kinetic energy increases as the magnitude of the velocity increases, which also makes sense. And again, our drag force affects the kinetic energy, since the force times the distance is going to equal a change in kinetic energy. So again, this all makes sense, and thank you for watching my final lab.